Right, good evening, everyone. I hope you can hear me at the back. Someone wave if they can hear me at the back. Yes, okay, good. We're here for the Cirencester Science and Technology Society public lecture. We have one each year. We have private lectures once a month, but tonight we're here for the public lecture. Done a bit of a shortcut with my counting. And I think we've got about 100 people in the lecture theatre this evening. What's our count on Zoom, Richard? 150. That's a nice number. Okay. The most important items this evening are fire exits here, here, and here. Toilets here, very important. Seatbelt optional for this evening. Very interesting lecture, like most of the lectures that we hold this evening. I'm going to hand over to Malcolm in just a minute to introduce our guest speaker for the evening. But very, very interesting session. It's my first lecture as chair of the society. And what I've seen over the last few weeks is the amount of effort that goes in from the committee members to bring these events together. So a big thank you to the committee for making this happen this evening. And Malcolm, over to you for introductions.
Thank you. Well, ladies and gentlemen, it gives me very great pleasure to introduce tonight's speaker, Professor Marcus de Sautoy, who has an OBE and is Fellow of the Royal Society. He's a British mathematician and author of many popular books on mathematics and science. He was awarded the title of distinction of Professor of Mathematics at the University of Oxford in 2008. He was appointed the Charles Simonyi Professor of for the Public Understanding of Science and a fellowship at New College latterly, and he's also formerly a Fellow of All Souls College, Oxford, and Wadham College. He's previously the President of the Mathematical Association, an Engineering and Physical Sciences Research Council, Senior Media Fellow, and Royal Society University Research Fellow. Now, many of you might know Marcus from his appearances on either radio or television. He's presented the BBC4 television programme Mind Games and co-hosted the TV series School of Hard Maths with Dara O'Brien. On the latter show, he posed mathematical questions with real-world applications, and O'Brien and a guest then tried to solve the problems using rigorous and experimental methods, respectively. In 2006, interestingly, Marcus delivered the 2006 Royal Institution Christmas lectures for children. And this is only the third time that mathematics has been the topic for this, this series. And it was under the number 8 of mysteries. On the first occasion that maths had been presented in 1978, when the lecture was delivered by Eric Christopher Zeeman, Marcus was then a schoolboy and in the audience. So without further ado, I'll hand you over to Professor de Sautoy. Thank you, Marcus.
Thank you. Well, thank you for all coming out. I've got some a microphone, so I hope you can all hear me at the back without me having to do too much shouting. Tonight, I want to give you a kind of choice. You can either take the long route. It's boring, laborious, nothing particularly interesting. Actually, might be a little bit dangerous. Perhaps a few animals on the way, might have to try and avoid. And it's just going to take you forever, and a lot of effort. Or there's an alternative. I'm going to show you that there could be a shortcut to many of the problems that you face in life and in mathematics. And so I'm going to be encouraging you to not to do the long, laborious, boring way, but to take the exciting, fast shortcuts. So this is actually the topic of the book that is being sold, hopefully sold out soon at the back. My new book, Thinking Better, The Art of the Shortcut. And in a way, this is a celebration of my own subject of mathematics, which I really believe deserves to be called the art of the shortcut. It's the book gives kind of whole suite of ways of thinking that we've developed over the last 2,000 years of mathematical exploration to see if you look at a problem, actually very much in the spirit of the program that I did with Dara O'Brien, the School of Hard Sums, where the other comedians came on and they did things the kind of slow, boring way. And Dara, who is trained as a mathematician, knew all these cunning shortcuts and would show these other comedians up by his incredible skills. So I actually was, when I was a school kid, one of the things that made me want to become a mathematician was partly going to the Christmas lectures that Christopher Zeman gave. He really just showed how exciting mathematics was. But also the teacher in my school, I actually grew up in Oxfordshire, my comprehensive school, the teacher told us a story one day, which kind of revealed to me the power of mathematics to shortcut doing hard work. And it was the story of a young Carl Friedrich Gauss. Some of you, I can see a few nods, you know the story because I'm going to tell you. This is a very kind of apocryphal story that we mathematicians are brought up on. This is actually quite a young picture of Gauss, but the story relates to when he was at school, aged 8 or 9, and there were about 100 students in one classroom. And the teacher that morning decided he wanted to have a little bit of a rest, get the kids just working hard, and he could have a little kip at the back of the classroom. So he said, he came up with this challenge for the school kids that they had to add up the numbers from 1 to 100. And he thought, well, this is going to take them forever because they're going to go 1 plus 2 plus 3 plus 4, and he should be able to get about 40 minutes sleep perhaps. But even before he'd finished challenging the kids in the class with this seemingly very boring, laborious problem, the young Gauss had already written a number down on his chalkboard and slammed it down on the teacher's desk. And the teacher thought, you know, what is this impudent student claiming to just written down some random number on the board? But when he looked at the number, there was the right answer staring at him. And he was so surprised. Well, how on earth did you manage to do all of that hard work so quickly? And Gauss said, well, there's a shortcut, because you don't have to start at the beginning of the journey and just, you know, laboriously try and climb the mountain. You know, if you did that, adding numbers up, after a while, I'd probably make some arithmetic mistake, take you a long time. He spotted a clever way to do the sum. He said, well, why don't you take the first number and the last number, sort of do the journey from both directions. And so if you add 1 plus 100, that's 101. If you add 2 plus 99, that's also 101. 3 plus 98, 101. What he saw was that there were 50 pairs of numbers, all adding up to 101. So that was why he was able to write down the answer very quickly. It's 5,050. And when my teacher told me this, this little trick, I think that was one of the moments when I suddenly thought, wow, this is the subject I want to do. Because, you know, as a teenager, I was pretty lazy, like most teenagers. I wanted to do a subject where I didn't have to do much work. And I could see this one, wow, this seemed to be a whole suite of clever ways where you can do the sum really quickly and then go out and play football. And my teacher, I remember him saying, you know, at the end of that story, what I'm going to teach you, mathematics, this is the art of the shortcut. I'm going to tell you all of these wonderful ways we've discovered to look at problems and find a sneaky way to sort of walk the journey from end and the beginning at the same time to get the right answer. And I think the beauty of this little story is that even if the teacher had said, oh, okay, I'm going to make this really difficult, I'm going to ask you to add up the numbers from 1 to 1,000,000. You know, the rest of the class will be, oh my gosh, this is going to take a very long time. But Gauss can play the same trick. This trick shortcuts however hard you make the problem, however many numbers, the same trick of pairing the numbers up will very quickly give you the answer. So it was this point when I fell in love with the subject and say, oh, yeah, I'm going to dedicate my life to the art of the shortcuts. And it's interesting sort of tension here because, you know, these shortcuts are trying to help you to avoid doing work. But actually, many of you probably enjoy working. It's part of our identity quite often. But for me, what's important is that you want to dedicate yourself to doing work you enjoy doing, not boring work where actually the aim is just to get to the end of the journey and you're not enjoying the kind of the walk on the way. And I think I quite like this division that Aristotle came up with two different sorts of work. He said there's praxis, which is work for its own sake. That's the work that you love doing. I love doing mathematics. I don't mind spending a lot of time at my desk working at mathematics because it's something I really enjoy. What I don't like is just work for an outcome where I have to do a lot of hard work just to get the outcome. It's there that I want the shortcuts so I can actually get to the work I really want to do. I don't want to spend time doing work that is boring, laborious, not interesting, but has to be done. Either get a computer to do it or use one of these shortcuts. And the point is that the computer often is not very good at coming up with the shortcuts. I've also brought some copies of my previous book called The Creativity Code, which is all about the power of artificial intelligence to do extraordinary things, including being creative. And this new book is partly a response to that book, because I remember giving an interview to John Harris at The Guardian about the power of AI in this modern age. And by the end of the interview, he was so depressed because it seemed like, oh gosh, what is there left for humanity if it can write, symphonies and novels and poetry? And I said, well, I think, so I had to cheer him up basically. So I thought, well, actually, I think what we've got going for us as a species is that we are basically pretty idle. We like avoiding boring old hard work. Computers don't get tired. This thing can just keep on going, provided it's plugged into the electricity, I guess. But it doesn't get tired. We get tired and we want to, but that kind of pushes us to kind of find clever ways to do things. So I think that's somehow our saving grace, that the computer, if you gave it adding up to 1 to 1,000,000, it will just go through that. There will be some point where it peters out, but it won't come up with a clever way of thinking about a problem. So I'm after avoiding work for an outcome by using these shortcuts, so I can spend my time doing what I want to do. And actually, Karl Marx always believed that in a higher phase of communist society, labor has become not only a means of life, but life's prime want. But actually, we'll be working because we want to work. So these shortcuts are trying to get you to that sort of Karl Marx's ideal of work for something that you want to do. So what I want to do is to take you through a few of the shortcuts and some of the kind of highlights of how mathematics has been very good at finding clever ways to think about problems. I'm going to start actually with a shortcut that mathematicians weren't the first to come up with. In fact, nature started finding the shortcuts before we humans came on the scene, because nature itself is very good at finding clever ways to solve problems. So, for example, the bee, making a honeycomb, well, why doesn't it make squares? Wouldn't that be easier, or little triangles? It makes these kind of strange hexagons. Why does it do that? Well, the bee has actually discovered that wax is very expensive for a bee to make, but this particular design uses the smallest amount of wax to enclose a particular volume of honey. So the nature has already sort of found the shortcut. If you want to use as little wax as possible, is these hexagons that are the solution. It took us quite a little bit of time to mathematically work out that there wasn't a cleverer way to do this, but nature had already discovered the shortcut. If you don't want to use too much wax, it's hexagons that are the answer. Bubbles, again, why is a bubble, when you blow it, a sphere? It settles into a spherical shape. Again, nature is very lazy. It wants to use as little energy as possible. And the energy inside a bubble to contain that volume of air is proportional to the surface area. And a sphere is the shape with the smallest surface area to enclose that particular volume. So if you bulge it out, the surface area increases, it's more energy required to hold that shape. It rolls back down the hill and becomes a sphere. if you can actually use this to your advantage, for example, as an engineer, if you're trying to find a low energy shape for a particular building, for example, using bubbles is a very clever way, because, for example, if you put this frame inside a soap film and you pull it out, this is the shape that will be the lowest energy shape if you're going to create a sort of a building in this shape. So nature always sort of balls roll down and find the bottom of the valley to settle on. So this was actually used by Frei Otto, an architect, when he designed the Munich Olympic building. He used bubbles as his shortcut for finding the best way to do this. What he wanted, a very kind of natural looking canopy over the stadium, but he wanted it to be not too stressful on the materials, and the bubble showed him how to do it. And so we actually have a kind of saying in science, which goes back to Maupertuis, that in everything nature is thrifty. Nature is very good at finding the kind of low energy shortcuts to things. Indeed, even, if you think about the way light travels, light always finds the shortcut. It tries to find the path which will get it to its destination the quickest. And one example of this is this strange effect you get when you put your leg in water, and then or even you put a ruler in the water and the ruler seems to bend, because the light travels at different speeds in different mediums, and so it tries to get out of the medium that it's slowest in as quick as possible, so it can spend more time in the faster medium. And so already sort of nature is able to solve this problem. The light finds the fastest path. Now that's kind of curious. How does it actually do that? Because how does it know where it's going? How does it know to get out of that path? Well, we now think actually it's exploiting quantum physics. Quantum physics allows the light to try all different possibilities, and then it collapses into the low energy state, which is the quickest path out of there. So it's actually sort of experimenting by doing all the possibilities and then collapsing. And you can see this actually in the animal kingdom as well. For example, ants or slime mold, they're very good at finding these short paths to destinations. But often what they will have to do is to try out lots of different possibilities and sort of hone in on that, which is in some sense rather inefficient. I mean, quantum physics is quite clever to use that. But one kind of example of this challenge, actually, I think we gave this to Dara as one of the problems they had to do. So the comedians went out and actually demonstrated this on the beach and had to swim into the sea. So the challenge was, if you're a lifeguard and you see somebody out at sea, you can run twice as fast on the sand as you can swim. So where is the optimal place in order to enter the water so you can get to the drowning swimmer as quickly as possible? So you want to somewhere which is spending less time in the water, because that's where you're slowest. But so you could say, well, I'm going to minimize it as much as possible. So I'm going to run to the sort of perpendicular line coming down, but that means you're spending more time running on the sand. So actually that's a little bit slower. Finding this point where the optimal place to be able to run into and then swim into the sea, such you get to the drowning person as quickly as possible, is quite a challenging problem. You see, light would be able to solve that very quickly. But how do we find that optimal point? Well, we've come up with a clever tool which actually assesses a whole situation, and rather than like the slime mold or the ant or the quantum physics light trying all the different possibilities, this tool that we've come up with very cleverly hones in on the optimal place. And this is this wonderful shortcut that we invented by Newton and Leibniz called the calculus. So basically we teach our kids the calculus at university. We're still at school a little bit, because this allows you to look at a challenge and find the place which will either get you to the place quickest or maximize your profits or minimize the amount of energy spent on doing something. So although nature is very good at finding these kind of the fast way here using its methods, we had to come up with a different kind of strategy in order to find this optimal point. So Darrow was actually faced with having to do a bit of calculus in order to solve this problem. It turns out that animals are quite good at solving this. Is this evidence that dogs, you know, for example, if you, there was somebody who did some experimenting, threw a stick into the water and kept on measuring to see where the dog entered the water in order to get to, and the dog very quickly honed in on the optimal place to enter. And the guy wrote a paper saying, you know, my dog can do calculus, which, you know, so actually in some settings, we do build up an intuition to be able to solve these problems without having to do the actual kind of calculations on the page. But sometimes you do need to do those calculations. And one of the challenges that the mathematicians at the time of Newton and Leibniz, when they came up with this fantastic tool, was finding the best kind of curve for a roller coaster ride. I'm not sure they were really trying to make roller coasters in the 17th century, but I'm not sure when the first roller coaster. But essentially, they were interested in the challenge of what is the shape of the curve if I roll a ball down that gets me from A to B the quickest way possible. Maybe it's just a straight line, or maybe it's some sort of quadratic that goes down to the bottom. And so this was one of the challenges. Can you work out what's the curve which gets you fastest the ball from A to B? And it turned out to be a very strange curve. It's actually a curve that if you take a bicycle wheel and you sort of put a pencil on the bicycle wheel and you draw the shape that you get if you wheel the bicycle wheel along, this is the shape if you turn it upside down, which is the fastest roller coaster ride that you can make. Now, actually, it does something rather counterintuitive because it goes below the level that you're trying to arrive at. So actually, at the end of the journey, you're sort of slowing down because you're accelerating up a little hill to get to your destination. So it was quite a counterintuitive kind of curve that the calculus came up with to solve this problem of how to get to A to B as quickly as possible. And if you give people a choice, they generally don't choose the one which looks like you're having to do a lot more work. You're going down and then up again. But of course, you're actually building up speed, which you're using at the end to actually get to your destination quickly. So this was an example of how calculus helped us to find a shortcut to the fastest way to get from A to B, which was pretty counterintuitive. So nature does things very well. We have to use this tool of the calculus very often to find this shortcut. So this is the shortcut I've called the differential shortcut, the power of calculus to hone in and find the best solution to something without having to experiment and try lots of things out. One of the things we're faced with in our modern age is this kind of onslaught of data. We're being kind of bombarded with numbers, trying to keep track of things. And mathematics has come up with very clever ways to find the kind of pattern inside data, even though there might be millions and millions of data points. How do you find out what's really going on inside there? So this is very useful because rather than trying to understand thousands, millions of bits of data, how much do you really need to look at to know what's going on in a particular problem? Now, some of you might remember this advert. I remember this as a kid, where Whiskas cat food claimed that 8 out of 10 cats prefer Whiskas. Now, I was very intrigued by this as a kid because we had a cat at home, and I don't remember anybody ever coming and asking our cat what sort of cat food we like. So I thought, well, how can they be so confident if they haven't asked our cat? Now, I was wanted to know how many cats had they asked in order to be able to confidently make this claim. And when I got up to university, I began to learn the tools which allow you to tell what sort of sample you need to look at to get a feel for what's going on. I mean, there are 7 million cats in the UK. How many cats do you think you would have to ask to actually to be pretty confident in making that claim? Well, for example, generally, this is the sort of standard you're going for. You want that in this sample, 19 out of 20 times the sample you will take is within 5% of what the actual value in that 7 million cats is. Now, I would say that, okay, 19 out of 20, that's quite strong and only 5% error. I was quite surprised to discover that the sample you need to take to have that kind of confidence in 7 million cats is actually only 246 cats. That's a remarkably small number of cats to have that kind of confidence that actually you've got a good intuition now for a good basis to support your claim that 8 out of 10 cats prefer whiskers. So this is really useful because this means that you don't have to waste a lot of time asking thousands of cats out of those 7 million. I mean, I would have said you'd have to do, like 5,000 to be that confident. 246 is amazing. That will 19 out of 20 times, a 246 sample of 7 million cats will be within 5% of the true value. That's a really important shortcut to know, that when you've got a data set, provided you're doing the data set without some sort of hidden bias in it. Of course, this is one of the problems, a very famous, you're taking political polls. We've already seen many times political polls getting things wrong. In the past, there was a very good example where they phoned everyone up in the 50s to ask what they were going to vote in America, not realizing that it was only people with a lot of money that had telephones at that time. So you have to be careful when you're doing your sample, you're truly randomly sampling them. But there's another, knowing how much data to look at is quite important kind of skill in order to be able to not waste time on doing too much. I think there's a nice example in a kind of game show scenario, like Deal or No Deal, for example, where you have boxes and you have to see, well, how many boxes do I need to kind of open before I get a good sense of what the data looks like. In fact, this version of Deal or No Deal, you actually, in Deal or No Deal, you know the values in the boxes. But what if you played a game where actually you don't know how much money is in any of the boxes? Maybe there's just, like pennies in each box, or maybe one of the boxes contains 1 million. And so if you knew nothing about the prices, the prizes in each of the boxes, how many boxes would you have to look at before you made up your mind, okay, yeah, I'm going for keeping on this box? And this is an example of a kind of problem we have that arises many times in life. I mean, if you're looking for a restaurant and you're going down the high street and you look at one, yeah, that looks quite nice, but let's try and see if there's any nicer restaurants, or looking for your first house to buy. You see this wonderful house on the first go, but you think, well, maybe there's more good stuff out there. I think the worst one is your partner for life. You go out with your girlfriend or boyfriend from school and they're fantastic, but you begin to worry, well, I haven't seen the rest of the field, maybe. And generally you can't go back. You chuck your girlfriend or boyfriend, it's quite hard to go, actually, you were the best. It don't really work. So mathematics has come up with a clever way to work out how much of the field you need to see, whether it's boxes in this game show or houses, before you should actually take the next best thing that you see. And it turns out it's one of mathematics' kind of favorite numbers. So probably top of the top 10 numbers is pi. Pi comes up absolutely everywhere. But so second on the list is this number e, which starts 2.71828 and again goes on to infinity without any patterns. Very connected with natural logarithms, kind of exponentiation as well. But this number is the key to the strategy for how much data do you need to see before you make a decision. So when you analyze this problem mathematically, it turns out you want to look at the proportion of 1 over e of the whole thing that you're trying to assess. So let's take those boxes in this new version of Deal or No Deal. 1 over e is about 0.37. So it's 37%. You've got to look at 30% of the data, 37% of the data. So that gives you a good idea of what the lay of the land looks like. And then after that, the strategy is to go for the best thing that you see, which beats everything you've seen up to that point. Now, of course, it's possible you might have seen the best thing, but 1 out of 3 times, this will guarantee that you'll end up with the best thing. Okay, I can't guarantee that the first girlfriend or boyfriend was the right one, but this strategy says, no, okay, I'm going to do this mathematically. I'm going to look at 37% of the possible people I could go out with, and then after that, I'm going to choose the person who beats all the people I've been going out with since then. If you use that strategy, don't show your calculations to your partner. But this gives you a way of how much data you need to see to get the optimal strategy to get the best out of those boxes, flats, restaurants, or partners for life. So mathematics is very good at taking, knowing how little you can get away with in order to know what's going on in a large data set. Diagrams is another fantastic kind of shortcut. And I think for me, often when I'm doing a problem, I can actually visualize it or crystallize it in some sort of diagram. I find it's a very good way to kind of see what's going on in a situation. And very often, if you think a diagram, it's all about throwing away information. What's not important to this? Crystallizing the essential quality of a problem such that you can see what's going on. And one of the most famous diagrams which really changed policy in Britain was a diagram that Florence Nightingale used to persuade government to change its policies during the Crimean War. She went out and was a nurse and was seeing terrible deaths happening in the soldiers. But the deaths weren't happening because of being shot at. It turned out they were just dying in the hospitals. And so this is the year 1854 to 1855 on the right-hand side, and the kind of the large petals that are growing out of this. The center ones are deaths from things like actual battle, but most of the deaths are just happening in hospital. But then when the sanitation committee came and they realized that what was happening was, it was the bad health conditions of the hospital that was killing all of the soldiers, not the battles. And they cleaned out all the latrines, and suddenly the deaths completely went down inside the hospitals. And Florence Nightingale realized, that's what's killing our soldiers, is this bad sanitation. And she went back to London to try and persuade Parliament to take seriously sanitation in hospitals. And she started by trying to persuade them by talking to them, writing things, and she couldn't persuade them. They were just ignoring her until she constructed this diagram, one of the first kind of pie charts Florence Nightingale made. It's called the Rose diagram. You can see it actually if you go to the Florence Nightingale Museum in London. They've got a copy of the diagram there. And it was this that helped change policy, and the politicians realized, yes, they could see in this diagram that when the sanitation committee and they cleaned the hospitals out, suddenly the deaths went down. This is what persuaded the government to change its mind. The diagram just somehow a diagram just shouts out. It's very hard to unsee a diagram once you see what's going on. Actually, there's an example of a similar sort of policy using the visual world to persuade government to do things. I once had a guy from America who's responsible for pandemics in America. This is before our pandemic. And he was trying to persuade government to take, in America, to take the threat of pandemic seriously. And he wrote a massive, great document, which he sent to the politicians in America. And of course, nobody read it. And he realized, okay, I need to write a smaller document. So he wrote it like a 5-page article, which he gave it. Still, nobody read it. And then he said, okay, what have I got to do? I've got to make a movie. So he actually was one of the people who made with Matt Damon the movie Pandemic, which suddenly woke up all of the politicians to what could happen. And that movie is pretty accurate because he was the scientific advisor for Pandemic. He was actually criticized afterwards. The other scientists said, all terribly accurate, except for one detail. There's no way in just a year you're going to find a vaccine. And that just isn't real. It takes 10 years to. So I talked to him recently, so I was very pleased actually to see actually even that prediction I got right. But the power of a diagram, actually, I think to illustrate what's going on is really one of our best shortcuts. But you need to be careful here because sometimes you get very tempted to put too much information in the diagram. I mean, think of map. A map is a great tool for shortcutting, trying to understand how to navigate your environment around you. But you want to make sure your map doesn't have too much detail in it. If it starts to have too much detail, then it becomes not so useful. And I love this map that is actually part of a story that Lewis Carroll wrote, of course, famous for Alice in Wonderland and things. But this was about, it's called Sylvie and Bruno Concluded. This land had a map. It was so good. It says we actually made a map of the country, and it was on a scale of 1 mile to 1 mile. It had every detail in it. It was just everything. So have you used it much? Well, it's never been spread out yet. The farmers objected. They said it would cover the whole country and shut out the sunlight. So we now use the country itself as its own map. And I assure you, it does nearly as well. And actually, I think Borges as well writes a story where they create a map, which is a 1-to-1 copy. And then actually, that isn't very useful. This is very important. The best sort of scientific diagrams are those which sort of pick out the essential quality of the problem and throw away anything that's not important. One of the best examples, I think, was the picture in the nature diagram of the discovery of this double helix of DNA. Actually, when Crick and Watson started to first try and draw a diagram of what they discovered about this double helix in DNA, they were too tempted to put in all of the extra things they discovered. They wanted the structure of the molecules and things there, and it was a complete mess. And eventually, Crick brought this little picture that they were doing home to his wife, who was an artist. She mostly did portraiture, but she looked at this diagram and said, well, what's important about it? And eventually, she threw away all of the things that weren't important. And this very famous double helix spiral that's in the Nature paper of their discovery is done actually by Odile Crick, this artist, who threw away everything that wasn't important to be able to crystallize what is important. Now, I think the best diagrams, we use diagrams to understand the incredibly big things in the universe, incredibly small, yet we bring them into this realm where we can draw them on the page. So I think Copernicus wrote this long treatise on trying to persuade everyone that the sun is at the center of the solar system. What persuaded everyone basically was this little picture that he drew quite early on in the manuscript. And of course, it isn't a geometric representation of the planets. They don't do perfect circles. They do these ellipses. They're not beautifully spaced out like that. But this diagram crystallized what he was trying to persuade people, that the sun is at the center of this. And go into any chemist's lab, it's full of these little lines and little H's and C's and O's, the structure of molecules. Particle physicists had been trying to understand particle interactions with hugely complicated mathematical integrals and things, these path integrals. It was a complete mess until Feynman came along and said, I just don't understand this. It's too hard work. And he came up with these beautiful little diagrams, which actually are just coding up what these integrals are doing. And it's these now that any particle physicist will use in order to understand how particles interact. But a diagram, because you're throwing away information or representing information perhaps in a kind of new way, can be dangerous. And there are some very bad examples used, especially in the media, where people draw a diagram to try and make a political point, but kind of hide in the diagram some feature which would reveal actually it's completely opposite to what they believe. So this was one that was used by Fox News. They're generally Fox News is responsible for all the crappy diagrams. But what the diagram they used was to try and illustrate the impact of tax cuts that I think Bush was proposing to make. And the diagram they used is the bar chart on the left here. And it looks like a big difference in they do these tax cuts and look what's going to happen to whatever this is measuring. I can't remember what it was measuring. But actually what you see is that the axis doesn't start at 0, it starts at 34. You don't see that. You think, oh yeah, it's a big difference. But actually, if you plot it with 0 at the bottom, you see that the difference relative to what you're trying to measure is incredibly small. So this is a very classic example of putting your axes in the wrong place to make things look much bigger. Here's another one. This is company profits. And so company C, to show that they're doing incredibly well, will often do this trick. So they'll say, oh, look, company A, only 1 million profits this year. Company B, 2 million, but we're on 5 million. But you see what they've done? they've also expanded not just the height, but the width. So to put at company A to cover the profits of company C, you need 25 company A's to cover that square of company C. So another clever trick, which looks like, oh yeah, it's just the height, but they've also expanded the width. So diagrams, you have to be careful a little bit. You can kind of abuse a diagram for your political gains. So I think diagrams, for me, are a very powerful way of trying to understand what's going on. I think data, we're being overwhelmed with this in this kind of modern age. The other thing that I think we're being challenged with is trying to find our way around networks, because increasingly we are a very networked society, and trying to understand how that network is working, trying to find tricks to navigate that network is, increasingly important. And if you think about it, one of the best shortcuts that we've ever come up with is the network to find the particular website that you're interested in. I always find it magic. I just start typing into Google and somehow it already knows where I want to go. And it's not Google elves sitting there going, I think it wants this one. It's an incredibly clever bit of mathematics that Larry Page and Sergey Brin learnt when they did their maths degrees at university. It's something called eigenvalues of matrices, which are used to actually find in this massively complex network the places that you want to visit. But actually, we've been navigating networks for several hundred years in clever ways. And one of my favorite stories, and another story I think my teacher told me when I was at school, it's kind of one of these mathematical fairy tales. It's the story of a town in northern Germany, Prussia as it was called then, in the 18th century, called Königsberg. It's where Kant went to university, I think was born actually, grew up. This town is rather special because there's the River Pragel, which comes in, two branches of the river come in. Then there's an island in the center of the town, actually where the university used to be. And then the rivers join and go out to the Baltic Sea, I think. And there were 7 bridges crossing the river, and the residents of Königsberg of a Sunday afternoon would challenge themselves at trying to see if there was some way to cross each of those 7 bridges once and once only, and then to come back to the beginning again. But every time they tried to do these bridges, they'd always say, oh, there's one bridge we haven't been able to cross. But there was always this sneaky feeling like, well, maybe there's a way we haven't tried. How many different ways are there to do this? But it took one of the other great shortcutters of history, Carl Friedrich Gauss. Actually, I use as a kind of companion through the book because he seems to have a part to play in every single story I told of shortcuts. I would say he's the master shortcutter. But another great mathematician who found a shortcut to this problem is Leonhard Euler. He was in Russia at the time. He was a Swiss mathematician. And he heard about this story, asked to see the map, and then was able to prove why it was impossible to do this task. And what he did was to use, again, a diagram. So instead of these areas of land and the sort of complex kind of layout of the geometry, he used what we now call topology, another great shortcut. It's the way these islands and land masses are connected with the bridges that's important, not the actual geometry of the land. A bit like the London Underground map is not a physical geometric map of the way the stations are laid out in London. In fact, if you look at a geometric map of the London Underground, you won't recognize it. And it was Beck's great kind of contribution in the 30s to realize, actually, all we need to know is how these things are connected. So I can push and pull the lines around, and then we get this very iconic map of the London Underground, which, I live out in Hackney, and the distance on the map from Caledonia Road to King's Cross looks the same as from Leicester Square to Piccadilly Circus. But I know it takes 30 seconds to get on one and 3 minutes to get the other. But I don't care about that. I want to know how the thing's connected. So this is sort of Euler's London Underground map of the bridges in Königsberg. And he realized, hey, look, if you're making a journey around these bridges and you want to cross each bridge only once, and all of the bridges have to be covered, this is a bit like the challenge of drawing this picture without taking your pen off the paper. So, okay, you've got to start somewhere, but once you've started, once you go to a point, You go in on one line, and then you've got to go out on another line. And the next time you come into it, it's a new line, and you go out on another line. So actually, most of the points in this map have to have an even number of lines coming in and out of it. There's only two places which can have an odd number, where you start and where you finish. So Euler realized that any map which is possible to navigate or draw can have a maximum of 2 places with odd number lines coming out of it. So if you look at this, each point has an odd number. A has 3 lines coming out, so that's either got to be the beginning or the end. But B has 5, D has 3, C has 3. So without having to try any of the possibilities, the computer will probably just try them all, list them, and say it's not possible. Here are the all. But we can look at that and say it's impossible to navigate that. And this, it means that you can challenge somebody. If you draw a really complicated diagram and say, can you draw this without taking your pen off the paper? All you need to do is count the number of lines coming out of the points. And if there are, say, if all of them are even, turns out you can always navigate this map and come back to the beginning again. So an interesting example of this, not too far from here, is Bristol. Bristol has quite a few rivers going around through it, a lot of bridges. Somebody worked out there are 50 bridges, something of that order. So it's quite challenging. You wouldn't want to try that. This wouldn't take you too long to cover all the possibilities. But 50 bridges to know that you can do it. So he drew the map and counted up the number of lines coming in and out, and sure enough, it was possible. So he spent, I think, a day and a half going over all the bridges, proving that it was possible. I got a chance, actually, when I was filming a program with the BBC to go to Königsberg and actually see the bridges that are left there. And in fact, what's interesting is that some of the old bridges are still there. The Allies during the Second World War bombed a lot of them, so a lot of them have been knocked out. There are a few left. There's a dual carriageway which now goes across. The university was bombed. It's a very grim sort of place. I mean, the rest of the film crew that I was with hated going here, but for me, this is kind of like going to mathematical Disneyland. I was like in my element. There's a new railway bridge which you can actually cross. It turns out now there are still 7 bridges. But now the arrangement of bridges is such that you can walk the 7 bridges of modern day Königsberg, which is the Russian town of Kaliningrad. So I insisted with the crew that we had to go and walk all 7 before we were allowed to fly home. So, but I think, there's, we have many important networks. I've talked about the internet, but our network of friends, for example, also important. But there's a very interesting quality of our network of friends. You might have heard of this thing, the 6 degrees of separation. If I choose one of you randomly, and then I choose somebody else randomly across the world, it turns out that we can find 6 people which connect them. So each one is the friend of the next one. They're the friend of somebody else. Amazing that the network of our acquaintances means that you can get from one place to the other with just 6 steps. And this seems to be a quality of a particular sort of network where, we know a lot of people in our local environments, a lot of people here in Cirencester, but you probably have a few people maybe got a relative in America or somewhere else. These combination of a lot of local connections and a few global connections gives the network a quality that if you take 2 points in that network, you can very often get from one to the other very quickly. So this is very useful to know, because if you're creating a network that you want to have that property, that it's not going to take you a long time to get from one place to another, using this kind of lots of local and a few global, what's called a small world network, is going to guarantee that you can find your way across any bit of the network very quickly. And so this was discovered. So here's an example where everybody knows the people next to them, but a few connections across this network will mean that you can get very quickly from anywhere in the network to anywhere else. And this quality turns up in a lot of different places, not just acquaintances, but also in the brain. It seems that our brain is networked in a similar way, such that one neuron can talk quite quickly to other neurons by using the fact that there's a lot of local connectivity and then a few global synapses, neurons across the brain. This is actually Gauss's brain. People were kind of intrigued. Why was he so good at all these shortcuts? Was there something special about his brain? And there's a suggestion that his brain maybe the network is really good, but it somehow was more folded, more convoluted than other people's brains. But one thing that mathematics is very good at is actually looking at itself and knowing when something is impossible to do. We've already seen, well, I'm going to skip that bit. I want to give you a chance to ask some questions. So one of the challenges we've seen that we can go over bridges very quickly, but there's a challenge that we would really love to solve, but mathematics has started to look at itself and say, actually, we think there's a sort of problem that actually there's no shortcut other than trying every single possibility. And one example of this, you may have heard of this thing called the traveling salesman problem. That this is a little bit like the challenge of the bridges of Königsberg, but now what you're tasked with is visiting all of the locations on a map and trying to find the shortest path. So each of the paths now, it's not just about connections, but now we're interested in geometry, the distances. What's the shortest path that will get you around this? This is actually, I do a gig at Glastonbury every year, and I'm quite keen to try and find the quickest way to get to all the venues, the stages. So I drew a map and paced out kind of the distances. And so I was kind of challenging my kids with, well, what's the fastest way we can get around this? Turns out this sort of problem, we believe there is no shortcut other than trying all of the different possibilities, listing them all and finding the smallest one. In fact, it's one of our great unsolved problems. It's something called P versus NP. And there is, in fact, $1 million prize for proving that there is no shortcut to this problem. We think this genuinely has a quality you can't avoid doing the hard work. And there are quite a few different sorts of problems like this, which have this quality that we think they don't have shortcuts. We're not too sure. There might be a shortcut. You'll win the $1 million if you find a shortcut, a clever way to find the shortest path here. But we genuinely believe that there's a complexity issue here that you can't avoid having to do all of the hard work. So $1 million prize for anyone who can find why there isn't a shortcut. And sometimes it's important to know there are no shortcuts because you don't want to waste your time trying to find the shortcut when there isn't one. But I think I ended with the book with a quote from Gauss because, I suppose I set off on my journey to be a mathematician because I was a lazy teenager and wanted to avoid doing work. But as I've gone on, I realized actually finding these shortcuts often is quite hard work, but it's hard work that I enjoy. I enjoy finding shortcuts. But my feeling is that, I want these shortcuts to get me to the kind of edge of knowledge so I can spend my time kind of doing the work that I really enjoy doing. And I like this quote that Gauss wrote towards the end of his life. He said, it's not knowledge, the act of learning, not possession, but the act of getting there, which grants the greatest enjoyment. When I've clarified and exhausted a subject, then I turn away from it in order to go into darkness again. The never satisfied man is so strange. If he has completed a structure, then it is not in order to dwell in it peacefully, but in order to begin another. I imagine the world conqueror must feel thus, who after one kingdom is scarcely conquered, stretches out his arm for others. So what I hope is that the book will give you the kind of suite of shortcuts which will allow you to get to the place where you can stretch out your arms and search for the kind of unexpected things in the darkness. Thank you.
So that's a whistle-stop tour through the world of mathematical shortcuts. Now, I'm sure there are questions from the floor. I'll try and organise them as best I can.
I think you can speak into this microphone. If you want. Right. Is this one? Yeah, that works.
Just have to hold the button down.
Yeah.
Okay. First question. Yes.
That's a shortcut. I was intrigued by the fact that the traveling salesman didn't have a shortcut, but so much stuff is delivered to us now by couriers. Is there a shortcut for them?
No. You see, that's, yeah. So I'll just repeat the question if people didn't hear. So this is a real world problem, the traveling salesman, because so much things being delivered, especially over the last 18 months. And I remember going to the Ocado warehouse and I made a program about algorithms. They had amazing algorithms inside the warehouse for sorting all of the goods such that it came efficiently to be packed and delivered. But they also were really interested in, okay, from here, we now want to send our driver on the most efficient path using as little petrol as possible. And we have algorithms which will get you sort of within a certain distance very often of the best solution. So we come up with kind of best case sort of algorithms, which are ones that they use. But actually, to find the true smallest value, there's something they would love to know. Another quality, the problem which has a similar quality is a packing problem, which is also something that they face. But you're going on holiday, you've got lots of different sized suitcases, and you've got the boot of your car. What's the best way to put, is it put the biggest thing in first and then the next one? That's quite a good strategy, and it sometimes works as an algorithm. Just take the shortest distance from your first place, shortest distance out of there. But there are networks where that actually ends up giving you the longest route, not the shortest route. So, and again, trying to pack a boot of a car we believe is a similar sort of problem to this. There is nothing better than trying all the different possibilities. There's another, there's another very interesting version of this, which is a book. I'm a big football fan. So this one is, because this is kind of cute, because, mid-season, you quite like to know whether your football team still has the chance of winning the Premiership. That's what we're obsessed with. I'm an Arsenal fan at the moment. We're always quite a long way. Obviously a Tottenham fan. But it turns out that in the past, when I was a kid, you got 2 points for a win, and you shared the 2 points if you drew. Turned out then there was a very efficient algorithm to work out whether your team could still win at any point in the season by distributing the points, whether they could come top. When they changed the system to 3 points for a win, but 2 shares, 1 each for a draw, then you don't know by the end of the season actually what the total number of points added up across. It could vary, that everyone could draw, that'd be the smallest number. Everyone could either win or lose. It turned out that this change caused the algorithm not to work anymore. And now we believe this is also a problem where you have to try all the different ways that teams could win and lose or draw in order to find out genuinely whether your team will have a chance to win the Premiership. So that small change kind of messed up the algorithm we did have and resulted in it being like the traveling salesman. Well, at the moment, that's not what's responsible, is the maths. Sorry. I think it's on. So,
is it working?
Yes.
You showed us a network diagram that inferred that through 6 people you know everybody has worked with. Does a similar kind of network model work for the propagation of the virus through?
Yes. Well, yeah, this is very important. I mean, that is one thing that, we have some very good mathematical models, and what turns out to, so of course, we've learned about exponential growth and the power of just one person needs infects 2, that will very quickly infect a lot of people. But what happens with these models, which sort of knocks out the, so it's interesting, 6 degrees of separation. You see there, you probably need a local connections. So that your global, of course, probably maybe that also is what contributed, because what happened is you had few people flying from Wuhan to Italy or to England, which produces those local ones. So that's quite an interesting question, actually. How quickly did we, what is the connection between us and case 0, for example, or us? But one thing that happens, of course, is as we get immunity and as we get vaccinated, this causes the dynamic to completely change. And so, that's what is very interesting about these models. So, for example, Ebola is too deadly. So, although it has an explosive beginning, it very quickly just wipes out people to carry on spreading the virus. So that's why we very rarely see, it's very frightening when an Ebola breaks out. And actually, I was doing a project on sort of pandemics, a theatre project, and I could see we kind of identified what the worst case scenario was, which is basically what we experienced, where you're not actually, you don't know you've got the thing for 5 days, but you're giving it to people. And that's about the worst case kind of scenario for this model for spreading things. So we kind of, but again, you know, the WHO is absolutely right. The only way we could really use our models is if we had data. Test is what the head of the WHO said. And the point was, although we had fantastic modelers, we didn't have the data, enough data to really know what the dynamic of this thing was.
Yes.
I've heard that bees are very efficient traveling salesmen in that they visit different flowers, perhaps the hive, and minimize their route.
Yes.
From the traveling salesman.
Yeah, we did actually. I did this in one program. Yeah, so it's about bees. Bees are a mathematician's favorite insect. You know, well, I don't know actually. Maybe it's a close call between the prime number cicadas that you know. There's these wonderful cicadas in America which hide underground for a prime number of years before they appear. I think I'd take those on my desert island. But bees are pretty second place for being very mathematical. So we actually, I went and did some filming of a research team that put these little cameras on the back of the bees and saw what tasks they did and set out a traveling salesman problem. And so, of course, they got to start by just gathering data. So, but they started to do that, and very quickly they worked out it was a clever arrangement of flowers that meant that the most obvious route was not going to be the shortest route. So they had to do a kind of long path at some point, which wouldn't be, I mean, the sort of obvious algorithm is just go to the next nearest thing. But this, we laid out a network, which meant that they had to find a rather unexpected route, and they indeed did find the route. Now, I think part of that is just what often happens is the animals would be trying things out, and so it probably found it a little bit by just trial and error. And there's evidence that once it finds a pretty good route, it's kind of locally found something that works best. It may not be the best overall, but it's good enough. So quite often you'll find that it will sort of find a pretty good solution, and which is what our algorithms do as well. The algorithms we have find pretty good solutions, but they won't guarantee you that it's the best. I mean, the other wonderful thing about bees is they then go and tell the hive where to go, and they do this waggle dance, which is basically using a bit of trigonometry. I mean, they basically tell the angle at which they, that's, they do too much wiggle, and then they go, okay, right, we've got to go 30 degrees north, and then so they are just extraordinary animals for being able to navigate the world mathematically.
Oh, she's there.
I've got a question from John Mulligan out in Newman.
Hello, John Mulligan. Yes, great.
What is your definition of an algorithm?
My definition of an algorithm. Well, it's a bit like a recipe, and one of the important things, and this is kind of the quality that we saw of that way that Gauss saw about adding up numbers, that essentially an algorithm should be a kind of recipe that it doesn't matter what data you give it, it will be able to kind of find the solution. So that's why algebra is a very powerful tool in constructing algorithms, because it says, okay, you want to add up the numbers from 1 to n. Well, we've got an algorithm. It doesn't matter what n is. It can be 100 or 1,000,000. The recipe will get you to that solution very quickly. So, for me, an algorithm has to have kind of the quality of it being able to apply in multiple kind of situations. It should be a reasonably simple recipe. It should also come to some sort of, it shouldn't get stuck in a loop. So you also want it to actually kind of arrive at an answer with whatever data you give it. Basically it's a bit like a recipe that can cope in multiple situations.
Yes. You mentioned AI earlier. Is there a particular math problem today, play prize type cohort, say, where you think a
breakthrough might be made by the application of neural networks?
Yes. So the question, if people didn't hear, was going back to artificial intelligence. Are there mathematical challenges out there that I think might be that AI might be helpful in actually solving? And that is actually one of the themes that runs through the Creativity Code book, because I've always used the fact that mathematics is a highly creative subject as my protective shield against why I don't think computers can do my job, because it's a lot of kind of intuition going into the unknown. They're very good at churning through lots of examples, and we've already seen some good uses of computers to solve challenges like the 4-color map problem. If I draw any map of the world, you can always get away with just 4 colors to color the country such that no 2 countries with a border have the same color. We had to use, in the end, a computer to check like several thousand particular kind of sort of building block maps in order to finally solve that problem. But that's not intelligence, that's just brute force. We did the intelligence, just told the computer. I think your question is really relevant today, where we're getting computers finding interesting new ways to do things. That book starts with a story about Go and the fact that this computer programmed to play a game, this Japanese game, Chinese game with black and white stones where you try and surround territory. It came up with a new sort of move through looking at the way the game works that has changed the way human players play that game. So I was very interested in that book. Okay, seems to be doing things of a quite innovative, creative nature. How soon will it be until we actually have it coming up with interesting theorems? And at the moment, I'm not seeing anything which I find particularly exciting coming out of AI. It's certainly proving theorems, but most of them are not interesting. For me, a mathematician is a bit like a story. It's a bit like a novelist. It's not about just doing all the different possible combinations of letters and words. You know, I think some people think a mathematician that I must be just trying to prove all the true statements about numbers and geometry. And that's not what I'm doing. I'm trying to pick out the things which I think are interesting and tell a really interesting story. So AI at the moment is just churning out lots of proofs, but most of them are just not interesting. And so it hasn't yet picked up the aesthetic quality, the things that get us excited about a mathematical journey. But I don't think it'll be too long before it learns what we like, the sort of maths we like, the kind of things where we go, oh, that's really weird. I wasn't expecting that to happen. That's really, you know, we get excited when one bit of maths turns into a completely different bit of maths. I think that, you know, maths is actually quite a new thing. It's, like painting is a very old thing, people in the visual world. So, but somehow maths, getting the experience to know what we might find exciting maths, I think AI will pretty soon start picking that up. But it's still quite a way off. I mean, I saw an exercise where it was basically trying to learn maths through sort of trial and error, and then it was given a GCSE paper, and it got kind of a 3 or something. So it's still, I'm not feeling too threatened yet, but the book is actually a sort of call to embrace AI as a great collaborator. There will be things that the AI will be able to do that are not things that humans are very good at, but there will be qualities that we're good at. And I think the combination, the book trying encouraging us mathematicians to take seriously AI as a good collaborator, rather than being terrified that it's going to put us out of a job. There was a question here. Yeah.
I was going to ask, I'm aware that in neural networks, you try and localize the best solutions, so you can have lots of solutions, but more efficient networks. So I don't know whether NP and probably also applies to the fact that trying to find the most efficient solution for a neural network, it might be impossible, or you might try every single one. Obviously, as neural networks get larger and larger, and more complicated to find that most efficient route must be very well.
Yes, that's very interesting. So yeah, the idea that neural networks are, you know, that a lot of the challenge is finding efficient routes through these. You know, are these kind of AIs and neural networks going to be faced with a kind of difficult challenge that finding these paths are going to be very difficult? Yes, I think, you know, one of the things that AI seems to be already taking advantage of is that kind of small world property that's of having kind of lots of local and a few global. So it knows that it can get around. You know, that's a quality I suppose you see what you want to do is the challenge of the traveling salesman problem. The algorithm has got to work on whatever network you give it. That's quite a difficult challenge. If you then say, okay, no, I'm going to limit the quality of the network, then algorithms start to appear. If the network has these extra properties, maybe there are ways to find the shortcuts. So I think that's what you want to do, is to say, okay, I'm going to make sure these networks are being built, not allowing everything, but with some constraints. And those constraints allow me for the algorithm actually to work in these cases. Anybody else? Oh, anyone else?
One of my favourite films is that where they have to displace the astronauts back to America. And they talk about using Euler's method being used to repromote. What is it about Euler's method?
Yeah, so the question was about Hidden Figures, the movie where the women are the calculators trying to work out how computers. That's right, exactly. That's the word. Yeah. So you sort of think, well, yeah, they were computing, and it's a wonderful film for celebrating women in mathematics, especially. I think, which is and there is, in fact, I talk about that film and the kind of breakthrough in the book, because I think it's a great example of that differential shortcut, which is, if we're sending a spaceship out into space, you want to make sure that this thing is going to go on the right path, and so you don't want to do it by trial and error. This is a case where you need to make sure that the thing is going to come back at a particular angles, not to get burnt up. And so Euler was one of the people in sort of generation after Newton and Leibniz who really pushed the calculus on to be able to find these kind of efficient paths through problems. So the Euler method is a particular method in differential calculus, which allowed the computers to identify the path which would just use the gravity, I think, to get the spaceship back. But it's a particular technique in differential calculus, which is exactly the challenge you're faced with all of the gravitational pulls, pushes and pulls, and the engine forces and things like that. So one of the challenges is that when you have more than two bodies with all of these gravitational pulls, it becomes a very complex problem to solve, something called the three-body problem. Anything three or more bodies, trying to find sort of stable solutions turns out to be very difficult because they tend to be chaotic. So that's one of the things, trying to find stable solutions. They are highly complex problems as soon as you have three things that you're trying to keep track of. Yes.
What do you find the most interesting unsolved math problem?
Yes, the most interesting unsolved math problem, which is, I mean, my area of expertise is symmetry and number theory. So these, and I think, if I had to choose one, it would probably be coming from number theory, which is about prime numbers. So my first book actually was called The Music of the Primes, and it's I wrote it because it was just after Andrew Wiles, my colleague in Oxford, proved Fermat's last theorem, and there was a wonderful book about the solution to this great unsolved problem, 350 years. But I kind of got this impression that the public thought, oh, that's the last theorem, they finished maths. Oh, great. So I was really keen to say, no, there's still loads we don't know. And I think, for me, it's very surprising that some of our most basic numbers, prime numbers, the indivisible numbers, they're kind of the atoms of our subject. Every number is made out of multiplying prime numbers together. So there are hydrogen and oxygen, and basically we would love to do what Mendeleev did, produce a kind of periodic table to tell us where each of these prime numbers are. First challenge is we have infinitely many of them. Second challenge is there seems to be no pattern to these numbers. They seem to be very rare. You can have a whole load of numbers with no primes, and suddenly you get a couple of primes, right, one after the other. And one of the great, we've got these problems called the millennial problems, which are $1 million prize for solving them. And the first one on the list is something called the Riemann hypothesis, which is trying to understand, are the primes genuinely got this random quality to them, or is there some pattern inside there? Again, it's a bit like the traveling salesman problem. We think that the primes genuinely have a randomness about them. Now, that's very hard to prove. If I could find a pattern, or if I could find an algorithm that found the shortest route, that's very easy to check. But proving that there is no pattern, proving that there's no algorithm, proving, like in Fermat's last theorem, that there's no solution to these equations, that's a really difficult challenge. So I would probably pick that one as, you know, I would sell my soul to Mephistopheles for a few years. Oh my God, Mephistopheles is here.
Why is it that prime numbers are so important for code breaking?
Yes, so why are prime numbers important for code breaking? So this is why we get money from the government, is because we say, oh, yes, our research is very important because we could crack codes. The interesting thing is the codes that are used on the internet, basically to crack the codes is the following problem. If I give you a number, find two prime numbers which multiply together, give that number. So if I give you 15, what are the primes which multiply together give 15? You shrug, that's easy, that's 3 times 5. If I now give you a 100-digit number or a 200-digit number, I'm asking you to find the primes. It's a bit like that traveling salesman problem. We do not have a clever algorithm to break the number apart, the 15 into the 3 times 5, if the number is too big. The only way is to try one number after another until we get an exact division. So this, if we go back to that chemistry analogy, the primes are a little bit like the atoms. In chemistry, you have this wonderful thing on the table. We also have spectroscopy, which says, give me a molecule, I'll tell you the atoms that make it using a spectrometer. We don't have a mathematical spectrometer. So the codes rely on, actually relying on the fact that we can't solve the mathematical problem. If I'm given a 200-digit number, it's like looking for a needle in a haystack. I can't find the primes which multiply together to give that number. So the codes that have been created on the internet exploit this property. Now, what's interesting is that the codes on the internet needed to have a special quality about them, because in the past, you would meet your secret agent, decide on the code, and go away with your 2 code books. But I can't go to Amazon every time I want to buy a book and get their code book. So we now have this thing called public key cryptography, where they send me one number which is used to encode my credit card. That's the big 200-digit number. I send that across this scrambled calculation. To undo the calculation, you need to know the 2 prime numbers which built that number. So this is a very beautiful lock where there's one key to lock your front door, but a different key to unlock it. One key to lock it is public, and it's, you know, Amazon, it's, you know, a public number there, 200-digit number. You can download it. If you want to crack all the credit cards that are going across the internet, you just have to crack that number into 2 prime numbers. I actually did some workshops in a prison, and I was telling them about this problem, and I could see the screws getting a little bit worried. Could I have a copy of that 200-digit number? So I said, it's going to take you longer than your sentence probably to find those 2 parts. But there's an interesting little coda to this, because it's a bit like how does light find its way efficiently through that path? It uses quantum physics to try all the different possibilities. We already know we can make a quantum computer, that the quantum computer sort of goes into superposition, and in each kind of multiverse or multiple worlds, it tries a different prime number out. And when you look at the thing, it's a bit like the light. It collapses into the state where the 2 primes actually divide. So we know that a quantum computer already has an algorithm which will quickly find these primes, because all the cases where it's trying where the primes don't divide somehow cancel each other out. And when we observe it, it collapses into this state with just the 2 primes kind of sticking out. So we already have the software, we don't have the hardware.
Time marches on. I think we'll take one more question, and then Marcus has very kindly agreed to sign some of your books. So you should don't regret that.
No, absolutely. Thank you for buying. So yeah. I will sit at the desk there and put a squiggle in the book.
Please go to ask the last question.
Right at the back. Go for it. Yes, so blockchain it uses a similar kind of technology to the kind of prime number kind of effect. But one of the things there is that you're using the fact that many people have checked the thing. So if you want to put a kind of cheat in, you've got to kind of correct over 50% of the people who put in the kind of that have checked. It's a real example of a community responsibility for security rather than having sort of one location for security. Is kind of what blockchain is exploiting. But they're certainly using some of the similar sort of maths in order to be able to do that.
Well, Marcus, thank you very, very much. I may have one question. As I was told some time when I was at university, that the problem is that nature is essentially exponential, but we tend to think all the time, our brains are geared to thinking arithmetically, and that's the problem. Would you like to comment on that?
Well, I think that in some ways we're beginning to experience the fact that nature might be exponential for a while, but then tops out. And this, in a sense, is what happened with the pandemic. But I think increasingly this is what's happening with kind of climate change and resources and things. So I think in the past we just thought there were kind of infinite resources and we could double our productivity, but we're beginning to realize we're now reaching a state where the planet cannot sustain our view that the world is exponential and that we can get double anything that we want next year, and we're starting to see limits appearing. And actually, I skipped over one bit, which is one part of the book is about. Let's see this. This is meant to be clever. And yeah, there we go. Is actually, I talk to people from a lot of other professions about their own shortcuts. I've got Brent Hoberman, who started lastminute.com. So startups, what shortcuts do they have? A cellist, are there any shortcuts to learning a cello, or do you just have to practice? But one of the people I talked to is an economist, Kate Raworth, who I actually recommended to come and talk. She's a fantastic speaker, but she's been trying to disrupt the many kind of simple diagrams we use in economics, which very often just expect exponential growth to increase. And she's now introduced something called donut economics. So she's the person I talk about in the diagrams shortcut, which says there are limits, and there's a kind of limits both globally for the planet, but also locally for making sure that nobody slips below the poverty line. And we need to keep track of these two things to stop actually our economic model generally thinking exponential growth will just go on forever.
Thank you. Well, I don't know about unexplored or unexplained theories, but certainly you've actually managed to achieve the impossible, making that, for me at least, interesting. Thank you very much indeed.